Thank you very much for coming today. We have Fiacre Rougieux from ANU. I practice about my French. He's a great scientist and good friend from ANU. He did his PhD on compensate silicon. He has a very nice or interesting finding about how compensation level influence the recombination and the mobility in this material. But today we'll focus on high efficiency N-type and how defects influence this one. So please welcome Fiacre.
Thanks, Steve, and thanks for having me here. It's a pleasure to come and have a chat about N-type silicon and how we can go to very high efficiency N-type solar cells using N-type silicon. And my talk today is just going to be about a few challenges that we encounter when we try to make high efficiency N-type solar cells. And just to show that N-type, yes, is more immune to impurities, but there's a lot we have to learn about if we want to go beyond the 25% efficiency mark. And basically, this is just a very schematic representation here, but what you see is just the efficiency as a function of lifetime, and this is our motivation here. This is for interdigitated back contact solar cell, and you can see that if you really want to have efficiency above 25%, you really need a bulk lifetime above 5 milliseconds, and typically that's very challenging because we don't, for standard industrial silicon, it's really rare to get that kind of lifetime, especially after thermal processing, which we see a lot of degradation. So really what we want to have here is we want to move from this red region, this low bulk lifetime, relatively low bulk lifetime, sub 5 milliseconds, and we want to go above this 5 millisecond mark towards the 10 millisecond mark so that we can reach those true high efficiencies. And so in doing this, the question is, what are the material-related challenges? What kind of defects are we looking at in this 5 millisecond range? And typically here, this is very different than standard P-type monocrystalline silicon solar cell, where the boron-oxygen defect we know is the main defect limiting the lifetime, or P-type multicrystalline silicon, where iron or dislocations or grain boundaries are the main limiting mechanisms. For N-type monocrystalline silicon, we don't have boron, we don't have, it's monocrystalline, and there shouldn't be much iron in there. So really, the question is, what are those defects present? And we can think that the defects that are going to limit the lifetime are going to be created during the growth of the ingot. So we're going to talk here about grown-in defects. And I'm going to start first a little review of what's been happening in terms of grown-in extended defects in N-type silicon and what we've learned in the past few years. So just a very simple recap. So this is a very schematic representation, but this is just to make sure that we all understand what we're talking about. During growth, two types of defects are created. Vacancies, as you can see here. So this is a silicon atom that's missing, and then we have silicon self-interstitial here. And basically this depends on the growth parameters. Okay? And we can also have foreign interstitial. Typically in CZ silicon, in Czochralski grown silicon, it's going to be oxygen above 1E17. And so these are the 3-point defects, the main 3-point defects. We can have other light elements such as carbon, nitrogen, hydrogen, but the main one is going to be oxygen for us. And then we have, apart from these point defects in monocrystalline silicon, we also going to have extended defects. And if extended defects are going to be dislocations, stacking faults, we can have also void and precipitates. And as we saw, because oxygen is the main foreign interstitial, apart from the dopant, those precipitates are going to be oxygen precipitates more often. So now we have a clear picture. Okay, this is what we think may limit the lifetime, but which defects shall we look for, and how process are going to influence those defects? Those are the questions we're looking at right now. How do we know if we have a vacancy or interstitial? Well, there's a very standard criteria used in the industry, in the silicon growing industry. That's used both for CZ and float zone silicon, and this is the Voronkov criteria. So this is the V over G criteria. So this is the basically the growth rate axial thermal gradient ratio, and that determines whether we're in a vacancy rich mode or in a silicon interstitial rich mode. And you can see it on this graph on the right here. In this graph, you have the growth rate here, and you have the axial thermal gradient in the x-axis. If for a constant axial thermal gradient, if we have a very high growth rate, so if we pull the CZ crystal very fast, we're going to have a vacancy-rich ingot. Okay? If we pull the crystal very slow, we're going to have a silicon interstitial-rich ingot. Okay? And basically, this is going to affect everything downstream. So if we have a vacancy-rich ingot, vacancy going to cluster together, and they're going to form voids. Vacancy going to enhance oxygen precipitation. So we're going to have a whole lot of mechanisms that happen during the ingot cooling after the ingot has been grown. And it's representing on the left here on this little graph that you can see here. For a high pooling rate here, we have vacancy-related defects. So there are D defects, typically void. And for very low growth rate, we have interstitial related defects, and and then we have the interesting region, which is the middle region, where we have both vacancy and interstitial related, and then we're going to have this typical ring structure that we can see in PL imaging sometimes, which is the oxidation stacking fault rings, and so. In this region, we have a central part that's vacancy rich and an external part that's interstitial rich. And in the middle, if we do a high temperature step or an oxidation step, we'll get this stacking fault. So, so the V over G ratio is what determines whether in vacancy and interstitial rich region. And in a typical CZ ingot that's used in a standard high-efficiency solar cells, we are in a vacancy-rich mode. And the same goes for float zone silicon. Float zone silicon ingots are pulled very fast, so they are usually in vacancy-rich mode. So we are in this region, okay? And we probably don't want to be too high. We want to be fairly close, so we don't have a overly high concentration of vacancies, okay? So now that we've established what we're talking about, this is just a picture of what will happen if we have both the vacancy-rich and the interstitial-rich region. And we'll have those different bands here, the P band, the L band, and the H band, which correspond to, H bands correspond to high concentration of vacancies. And then we're going to have lower and lower concentration of vacancy. And again, so basically our vacancy profile is gonna look like something like this, like a curve very high in the middle and then lower towards the edges, and then potentially we're gonna have interstitial concentration increasing towards the edges. Again, here V is the growth rate, G is the axial thermal gradient. So slow pooling rate, interstitial mode; high pooling rate, vacancy mode. Okay, so this is an optical macrograph image. So this image shows what happens if we start in a very fast pooling rate, a CZ ingot with a fast pooling rate, and then we slowly decrease the pooling rate of the ingot. What will happen? So as we start with a fast pooling rate, as we've seen before, we're going to have a lot of voids, or we have high vacancy concentration, so we're going to have a lot of voids. And then as we slow down, we're going to have still voids in the center, but interstitial at the edges. And then as we continue to slow down, we're going to have full interstitial rich silicon. And then as we even slow down more, we're going to end up with dislocation and other problems. So usually we don't want to be anywhere near here, but sometimes it happens, and it does happen randomly in ingots. So yeah, we want to be in this spot. That's where we want to be to avoid defects. So let's talk about oxygen precipitates. So as I said, when we're in this vacancy-rich region, we have a lot of vacancy, and vacancy enhances the diffusivity of oxygen. So it enhances the oxygen precipitation. And oxygen precipitates can be recombination active themselves. And that's what you see here. In this picture, you can see on the left a solar cell that's been processed, and it shows this ring-like structure with the center of the wafer that's got a lower lifetime here in this PL image. And you can see it on this lifetime sample here. The whole central region is really dead. And what happens is that those oxygen precipitates, as schematically represented here, really increase the recombination activity. So we really decrease the lifetime here. You can see here also, this is the lifetime as a function of injection level in this little graph here. As we increase the precipitate density, the lifetime decrease. So the lifetime is really dependent on the precipitate density. So there's a whole lot of factors that are going to influence this density, such as the cooling rate of the ingot itself, because if we have a slow cooling rate, we're going to have a lot of nucleation of those oxygen precipitates. And then if we do a high temperature process, we're going to have the growth of those precipitates, and the strain, they're going to become strained and recombination active. I think another interesting feature of those precipitate is metallic decoration. Like, it seems from recent results that those precipitate without metallic decoration are not recombination active, and you can see it here on this two graph here. On the left is a clean cell process here, and on the right is a less clean cell process. So basically, different chemical cleaning have been used, and the exact sisters wafer have been used here. But on the right, you have those typical oxygen precipitate ring, and on the left you don't have these kind of rings. So we have the same wafer, but because one was as metallic contamination, we activate those oxygen precipitates. So it seems that metallic are enabling the recombination activity, which is very important to tailor the cell process. Again, similar thing here. You start with an ascot wafer without rings in the middle, and then with a very short annealing at high temperature, you see this really ring-like structure and this degradation of the lifetime in the middle. This shouldn't happen because of the change in the oxygen precipitates. This is typically due to fast diffusing impurities, metallic impurities, decorating those oxygen precipitates and making them recombination active. This little graph here shows again that the recombination activity, so the inverted lifetime, is proportional to the strain precipitate density. So the more precipitate we have, the more the lower the lifetime is, and it doesn't seem to depend so much on the size of those precipitate, but rather on their density. Okay, so basically, when we have those oxygen precipitates, we are in this region that we were talking about, in this vacancy-rich region, and this vacancy enhances the diffusivity of oxygen, and therefore we have those precipitates when we process at high temperature. Let's talk about another type of defect that we can have is this stacking fault here, and the schematic representation here. Those really shouldn't happen in standard silicon, but if we are in this intermediate regime, we can have those ring-like structures that are more toward the edges of the wafer, and they enhance with oxygen precipitation too. So when we have oxygen precipitates, they build mechanical stresses on the lattice, and they generate those dislocation too. Those are stacking fault too. And typically we'd be around here in terms of growth rate. We'll be at intermediate growth rate. The worst scenario for us, and it does happen sometimes, is if we have dislocations, and we have dislocated monocrystalline ingots from time to time, and you can see here in this PLA imaging again those slip lines here or here. It can be also created due to too great amount of impurities, which is the case in here. But so yeah, if our pull rate is very slow, we can have the creation of dislocation, and we really don't want to be there for various reasons. And so yes, so if we have to think where we are situated, we'd be at very low growth rate, and we'll be in a region where we don't want to be. And this can also happen if we suddenly stop the growth of our ingot, and that will generate a lot of dislocation, which can propagate upwards in the crystal. So just to recap what we've seen so far, we've looked at different grown-in and process-induced extended defects. We've seen that oxygen precipitates are real concern for high efficiency N-type solar cell, and stacking faults also to a lesser extent, and dislocation to even lesser extent. But we have to keep in mind that all these extended defects can affect the lifetime. But really, it is possible that if we really tailor very well our growth process, we potentially can avoid generated all these extended defects. So if we're really in the sweet spot where we want to be, meaning not in the P band or L band, but really towards very low vacancy concentration, but not in interstitial regime, we can potentially avoid all these extended defects and avoid their effect on the lifetime. So the question is, provided that we overcome this challenge of the extended defects, the question is, what's next? What are the next defects limiting the lifetime? And this is represented schematically here. So this is the challenges and the efficiency as a function of challenges, material-related challenges. And if we overcome the challenges provided by extended defects, what's the next step to go towards above 25% efficiencies? What are the defects? And there's typically not a lot of literature on that. The question we're really asking here is, what are the defects between us and the intrinsic lifetime? This graph shows you a recent parameterization of the intrinsic lifetime in silicon. So this is the effective lifetime as a function of dopant density here, or bulk resistivity here. For a typical high efficiency N-type solar cell, we're going to be between 4 to 15 ohm centimeters. So we're going to be in this region here, okay? And what we can expect is 10, 20, 30 millisecond lifetime, okay? But what we really get for standard industrial wafers is lifetime sub 5 milliseconds. So the question is, we know that the potential is there, but we don't know what are the defects limiting the lifetime in this regime. So we want to be in this blue region here, but we're in this red region, we're in this low lifetime region, sub 5 millisecond here. And so that's a bit what we're starting to work on, understanding the defects limiting the lifetime above 5 milliseconds. If we go back to our challenges for mono N-type, we have a few ideas what could be those defects. They could potentially be metals in very small amount, or they could potentially be intrinsic point defects paired with light elements. And that's what we investigate in the last part, in the rest of this presentation. There's already literature on showing that point defects, intrinsic point defect, can limit the literature, can limit the lifetime or the efficiency of solar cells. And this one shows you just one type of defect, thermal donors. So basically, thermal donors are just a long chain of oxygen atoms, which are created around 450 degrees here. The first graph shows you the lifetime as a function of injection level here. And you can see that as we increase the thermal donor density from 1E15 to 5E15 per cubic centimeter, the lifetime decreased from 1 milliseconds to below 100 microseconds. So yes, thermal donors are recombination active. And you can see it in this other graph too. This is the lifetime as a function of injection level, and you can see that by removing thermal donor, which we usually are around 650 degrees, we can increase the lifetime. And they are also trapping center here. So we know for sure that some grown-in point defects, some point defect created during ingot growth can limit the lifetime. Now the question is, are there any other point defects limiting the lifetime? What are other point defects limiting the lifetime? Are they devacancy? Are they vacancy oxygen, vacancy hydrogen, vacancy nitrogen, or potentially interstitial related defect? We are not sure, and the literature on this subject is very small. So we're really at the beginning of something quite new and exciting. Before I go on to talk about those grown-in point defects, so before we're talking about extended defect, now we're talking about point-like defect. I'm just going to talk about how we're going to characterize those defects. And let's start with a small exercise. I mean, let's assume we have a lifetime of 1 millisecond, and assume we have a mid-gap defect with a standard capillary cross-section of 1e to the minus 14 square centimeters. So this is typical for a standard defect in silicon. What kind of defect density can we assume? Well, if we do the calculation, it's very simple. We find a defect density of 1e to the 10 per cubic centimeter. And typically, this means that this defect density is too low to be detected by deep level transient spectroscopy or electron paramagnetic resonance. So when we look at lifetime above 1 millisecond or 5 milliseconds, we won't be able to characterize the nature of those defects with standard characterization technique. So we won't be able to really tell the nature with standard DLTS, which is limited. It's usually 5 orders of magnitudes below the doping, and for a typical 1E15 doping, that's 1E10. So really we're sitting at the limit of standard technique. So this means we're going to need to use lifetime spectroscopy to identify the defect, or PL imaging, or other techniques that we use in the PV industry. And so that's quite interesting. Another point here that I'd like to make is that using standard passivation technique like silicon nitride or aluminum oxide to do the lifetime spectroscopy, we can potentially anneal the defect. Like if we do a 400 anneal to activate the aluminum oxide, we can potentially deactivate the defect. Or if we do a silicon nitride, we can potentially hydrogenate the defect. So we have to be careful where we're going to use passivation technique to study those defects, because potentially we're gonna alter the state of this defect, transform them, or change the complex themselves. So we have two strategies to overcome this challenge. Either we can use room temperature passivation, which I will present later on, or we can use a range of passivation technique with different hydrogen content in the film, or with different annealing temperature, so that we can really understand what are bulk defect and what are surface passivation effect. Okay, and this is quite important because too often we use control, or we use other type of wafers where the passivation can have an effect on the bulk lab itself. I have to note here, again, to emphasize that we're talking about really small defect concentration, 1 e to the power 10 per cubic centimeter. So it doesn't require much to hydrogenate this defect or to deactivate this defect. Okay, so that's why we have to be extremely careful when looking at these defects. Just presenting here quickly the setup we use in ANU to do a room temperature passivation. This is just a standard Sinton lifetime tester, and you can see it here in the fume hood. This is the lifetime tester here, and next to it we have a little container. This is just a standard plastic container, and we have a 20% HF solution in there. So we start by doing a surface preparation, typically RCA clean followed by TMAH etch to really prepare the surface, and then we put the sample straight into the HF here, and then we put it on the Sinton tester and then activate the passivation with light. So we create electron hole pairs, and that activates the passivation, and then we measure the lifetime using this. And this is great because we're really sure that when we do this kind of measurements, we're measuring the true growth conditions. So if you were to use a silicon nitride, you can never be sure that you're not hydrogenating the bulk, or you're not annealing some bulk defect. So this is really an advantage over silicon oxide, silicon nitrile, aluminum oxide passivation. Here we're really looking at the bulk. And also we got quite a low surface recombination velocity on a typical 1 ohm centimeter N-type wafer. Yeah. So yeah, again, this is a sample. This is the HF solution and the light activation here, and this is the standard. Assuming you're all familiar with the lifetime measurements itself. So let's look at how we use that technique to identify one defect in CZ silicon, in Czochralski grown silicon. Okay, so this graph shows you the lifetime here as a function of injection level here. And this is a standard CZ silicon wafer that's used for very high efficiency solar cells. Typically interdigitated back contact solar cells. And what we see is that we start with a lifetime of around approximately 1 millisecond here. And as we anneal it at 360 degrees for different length of time, so started 0 minutes, 20, 30, and 40 minutes, the lifetime increases. And this was very surprising for us, because had this happened for P-type silicon, we can think that this is potentially the boron-oxygen defect, or some metastable defect like iron-boron pairs or chromium-boron pairs. But here we are talking about N-type silicon, so there is only phosphorus and oxygen and what else? Some point defects. So the question is, what defect is deactivated at such low temperature? We could think potentially we're changing the state of thermal donors. So the next step for us is to do the same measurements at different temperature. And here again you have the lifetime here in microsecond as a function of injection level for 3 different annealing temperature. Here we're talking about half an hour annealing. And again the same thing happened at 450 degrees, 550 degrees, and 650 degrees. We know that standard thermal donors are annealed at 650 degrees, so at 650 degrees we can kill them all, we can remove them all, whereas at 450 they created. So because the same phenomenon appears, the same increase in lifetime from 1 millisecond to 4 milliseconds appears at all this temperature, we can be pretty certain that what we're looking at here is not thermal donor related. So it's related to other defects that are not thermal donors or not related to boron-oxygen, because there's no boron and oxygen, or metallic impurities. So I mean, you could potentially think it could be metallic impurities, but for metallic impurities to dissociate or to precipitate, we're talking here about very low temperatures, so it's very unlikely that this is what we're looking for. What we think more we're looking for is intrinsic point defect paired with light elements, because those complexes usually have quite low deactivation energy, so they can dissociate at very low temperature. And so that's what we did in this next experiment. What you see here is the remaining defect density. So this is calculated from the lifetime measurements. We do the lifetime, the inverted lifetime before and after anneal, and we obtain an effective defect density. This is standardly used. If it's 1, here it means all the defect is still present. If it's 0, it means all the defect has been removed. And here you have the remaining defect density as a function of temperature here. This is for isochronal anneal of 30 minutes. What we found is that after above 360 degrees, the defect is removed. Below 360 degrees, the defect is still present. This is quite low deactivation energy. And the next question was, well, can we relate this to anything we know? We can't measure this defect because we can't use DLTS or EPR, but perhaps we can use data of DLTS on other wafers to identify the defects. And there's been a lot of study using DLTS and irradiated silicon to create purposely vacancy oxygen, vacancy nitrogen, vacancy hydrogen. So there's a lot of data when there's a high concentration of defect created, and we can potentially use this data, compare it to our data, our lifetime data, and then try to figure out what is the nature of the defect we're looking at here. And when we did this, and so that's what I've added in this graph. This graph is not our data, this is data from the literature, from electron paramagnetic resonance. And you can see there's quite a different variety of elements paired with vacancy here. Here we just assume that we have a vacancy rich ingot, okay, because most industrial ingot are vacancy rich. And this shows the different dissociation temperature of those defects. So below 150 degrees, vacancy phosphorus are present, and then they are dissociated above 200 degrees, and etc. So we have vacancy hydrogen, devacancy, vacancy oxygen. And if we compare our lifetime result to the results from Watkins et al. On electron paramagnetic resonance, we find that what we see would correspond roughly here to vacancy oxygen, perhaps devacancy, considering the uncertainty that we have here. And so it's quite interesting that potentially, yes, in this wafer, vacancy oxygen or devacancy are potentially limiting the lifetime, which is an interesting finding itself. This is very early stage, okay, and we at the stage of verifying this through more thorough measurements. But regardless of the structure of the defect, or regardless of the nature of this defect, this is going to be very interesting because this is going to affect heterojunction solar cells. If we do a standard heterojunction solar cells, or like the recent IBC heterojunction solar cells, we're unlikely to reach the 400 degree mark because we have going to have this amorphous layer, and we typically don't need to go to high temperature because we don't do any diffusion. So we're not going to reach that temperature where we're going to deactivate this defect. So if we use the wafer as is, and we go through the heterojunction solar cell process, we're not going to deactivate the defect. We're going to have this low starting lifetime. And we think that for this particular wafer that we have here, which is not all wafer, but for this particular CZ wafer here, it would be beneficial to do a pre-anneal around 400 degree, 500 degree, to deactivate the defect before starting a heterojunction process. Of course, for a standard homojunction process, Because of the diffusion, this defect will be deactivated, so we don't have to worry too much about it. Although potentially we could recreate it at lower temperature, for example, during moduling or during other low temperature passivation step. Okay, so if that's clear, I'm going to move to the next section. We've seen here, like in the previous section, that oxygen not only creates precipitates, those precipitates put strain on the lattice and can create stacking faults themselves, both of which are recombination active and significantly degrade the lifetime. They put us out of the sweet spot where we want to be, the 5 millisecond sweet spot or higher. They also create thermal donors, which are recombination active, and they can potentially pair with vacancy and limit the lifetime. So really, we're asking ourselves, maybe we want to have an oxygen-free growth method, and why not use float zone silicon? Okay, of course, float zone is not such industry relevant at this stage because of ingot size and of cost, fabrication cost. But we can potentially think that for very high efficiency solar cells, there could be process simplification that enable the use of float zone silicon for high efficiency solar cells. And so that's our motivation to investigate a bit more what kind of defects are limiting float zone silicon and whether we can use them for high efficiency solar cells, especially considering that the recent interdigitated back contact heterojunction solar cells that we've seen recently are on Czochralski grown silicon. So it's quite interesting that it's a shift from float zone to CZ for a record efficiency solar cell. So that's our next and last step in this presentation, is talking about growing point defects in N-type float zone silicon. So nitrogen, first I have to start, why is there nitrogen in most float zone silicon that we grow? Well, nitrogen is used because in the IC industry or in other industry than the PV industry, we want to avoid extended defects and typically void or aggregate of vacancies, which are void, or aggregate of silicon self-interstitial. So we use vacancy, and as you can see here, nitrogen or dinitrogen, which is the dominant species in silicon of nitrogen, pairs with vacancies to form vacancy nitrogen complexes. I'm losing my words now. And those vacancy nitrogen complexes basically stop vacancy from aggregating and forming voids. So they really help in the IC industry because they stop the accumulation or the aggregation of point of intrinsic point defect. They really help having those structural or those extended defect, especially near the surface. Okay, we don't want extended defect in the surface in the IC industry. But the question is, well, we are the PV industry. We probably don't have the same requirement as other industry, and maybe void are okay for us. Maybe vacancy nitrogen pairs or nitrogen-related defects are recombination active. So that's really where we're coming from and what we want to learn here. Is it beneficial for us to have nitrogen here? We also know that nitrogen pins dislocation, so it improves mechanical strength at high temperature, and yeah. But for us, we want to know whether nitrogen point defect or nitrogen complexes can limit the lifetime. And what you see in this graph here is the lifetime here as a function of injection again, so you'll be familiar with this graph, plenty of them in this presentation, for 3 different wafers that came from 3 different ingots. Okay, so we have a 1.5 ohm centimeter nitrogen lean CZ ingot, typical ingot, 2.7 ohm centimeter nitrogen lean float zone, and then we have a nitrogen doped float zone. So this nitrogen doping came from the ambient. Okay, so the way the nitrogen comes from is we have typically argon and a little bit of nitrogen in the argon, and this is incorporated in the silicon using the float zone growth. Okay, and what we found is that the lifetime here is clearly lower, around 300 microseconds in the nitrogen doped float zone silicon, whereas it's around 4 milliseconds for the nitrogen lean float zone or for the CZ silicon. So that was quite interesting, and the obvious thought that we had is, well, nitrogen is obviously creating some kind of defects here, or is enabling the creation of some defect that are recombination active in the as-grown state. And the next question that we had is, well, nitrogen is creating some kind of defect. What happens if we were to put those wafers in a solar cell process? So we started simulating a high temperature thermal step that would be used for cell processes. And what we find, if we put those wafers at 1000 degrees for 1 hour, which is quite a high temperature, the lifetime improves. Again, lifetime injection level here. At 2015, the lifetime improves from 400 microseconds to above 2 milliseconds here, which is quite interesting. Note that we are still far off from the intrinsic lifetime. So this is Rougieux plus band-to-band here on top. So we still have some defect here, but we can improve the lifetime. So it seems that we are doing something to this defect when we are annealing it. And so we either transforming the defect or removing it. The question is, what is this defect? And as we've seen before, we can't really use DLTS or the techniques to identify the defect. So the next obvious step is to stick it under the PL imaging tool. And so this shows the lifetime, the spatial distribution of the lifetime as a function for aluminum oxide passivation. So you have the scale here around 600 microseconds. So this is a 4-inch wafer here. And what we see is that the lifetime around the edges is significantly higher than the lifetime in the center. So we have this radial symmetric distribution of the lifetime that's higher around the edges. The same happened with silicon nitride, but I have to say here, the scale was much higher. So the lifetime was much higher. We'll talk about that a bit later, but we can clearly see that there is this higher lifetime around the edges, which points that the defect density is lower around the edges. So what does that imply for the defect structure? From the lifetime measurements, from the spatial distribution of the lifetime, we are in low injection. We can extract the defect density as we've done before. So it's just the inverted lifetime minus the intrinsic lifetime, minus the inverted intrinsic lifetime. And so this is what this graph shows. So in the y-axis, you have the effective defect density in microseconds, in a microsecond minus 1, and this is the distance. So 4-inch wafer, like 100 millimeter wafer here. So this is the edge, and this is the center here, and you have the distribution of the defect density for both aluminum oxide and silicon nitride. And what we see is that we have this kind of distribution of defect like this, and this is typically reminds us of the distribution of vacancy in a as-grown ingot. So this is an indication that potentially what we're looking at is a vacancy nitrogen-related defect. Interestingly, we also measured the nitrogen with SIMS measurements. As you can see here, in the center and the edges, we had nitrogen concentration on the order of 4 to 5e15, 5e14 per cubic centimeter. But the nitrogen seems pretty flat. Okay, so if we have this radial, if you have this axial distribution of the defect density, it's potentially related to vacancy and vacancy paired with nitrogen. From the literature, there's a lot of different vacancy nitrogen complex. V2N, VN2, VN, so V vacancy and nitrogen. So there's a lot of different complexes that are potentially here. Our next and last question here was, is there one or is there many different vacancy nitrogen complex, assuming those are the complex we're looking at, limiting the lifetime? And what we can do here is use these little equations here. It's typically from Czochralski that's transformed here. So this we've plotted here the residual lifetime, so that's lifetime minus the intrinsic lifetime. So this is basically Czochralski lifetime as a function of the hole over electron ratio. And if you look at this equation, this is the hole over electron ratio here. If you find a linear trend in such a plot, it means you have a single defect. If you have a bilinear, or if you have multiple linear trends, it means that you have either more than one defect or a defect with multiple levels. Well, when we did this analysis on our lifetime curve, and you can see here for the silicon nitride or aluminum oxide, we find a bilinear trend. So there was no one single trend, there was multiple single trend. And this tells us that potentially there's more than one type of defect in these wafers, more than one type, meaning potentially VN2 or a V2N. We don't know the exact nature, but we know there's more than one type of defect. One final little interesting thing about this defect was when we passivated with aluminum oxide, and you can see here, we obtain lifetime around 400 microseconds. So this is our start. When we passivated with silicon nitride, we obtain lifetime around 4 milliseconds. And this is not due to surface passivation. We had plenty of control samples that showed the exact same lifetime with silicon nitride and aluminum oxide passivation. So here, the silicon nitride passivation and the aluminum oxide passivation is really similar. We have exact similar lifetime. What we're looking at here is not surface, but we're looking at bulk hydrogenation, and that's what we think. And I know there's been quite a lot of work done here on hydrogen passivation, but we think that with our standard nitride deposition, we are already hydrogenating significantly this defect, and it kind of makes sense in a way because remember we are talking about very small concentration of defects, so potentially not a lot of hydrogen is required to passivate this defect. But yeah, we know that the total hydrogen content of silicon nitride is 15 to 20%. So that's complex and atomic hydrogen, whereas it's less than 5% for aluminum oxide. So potentially the lower hydrogen content of aluminum oxide, or the lower atomic hydrogen content of aluminum oxide, leads to less bulk hydrogenation of the aluminum oxide, and that's what we think happens here. Again, we're doing more investigation to look at this, but it's interesting that not only we can thermally deactivate the defect at 1000 degrees, we can also hydrogenate it, and this is quite interesting. Again, for a standard amorphous silicon, or for a standard heterojunction solar cell, or even for a homojunction solar cells. It means that when we're going to deposit this amorphous layer, amorphous silicon layer, or silicon nitride layer, we can potentially enhance the lifetime if we tailor this hydrogenation process. So to conclude, we've seen that a lot of our range of extended defect can limit the lifetime stacking fold oxygen precipitate, can limit the lifetime of N-type monocrystalline silicon, and also the high temperature processes can increase the recombination activity by changing the strain defect density, or the having decoration of the precipitate by metals, which is quite interesting. And also we've seen that potentially you can have dislocation and slip lines, but those should not occur in high purity feedstock. But the interesting step is that we also think that not only extended defect, but also point defects, which are growth related, can limit the lifetime, and those are potentially just vacancy paired with light elements. Oxygen, nitrogen are the one we think are too likely candidate for CZ and FZ silicon. We also propose solutions to increase the lifetime. For CZ silicon, an annealing above 360 degrees was shown to significantly increase the lifetime from 1 millisecond to above 5 milliseconds. And for float zone silicon, we propose to use a high temperature annealing, typically around 1000 degrees, or a hydrogenation step to increase the lifetime. Just a final remark, concluding remark, is something we've learned in these studies, that we cannot trust a control wafer, and this has high impact for everything that we do in standard PV studies, because standard high temperature passivation or passivation processes are likely to affect the bulk lifetime, and this goes for CZ or float zone silicon. And I know that during my PhD, I used a lot of float zone control wafer, assuming that they would never change, be it for bulk study or passivation study. And this is not always true. This is not always true. And so there's no such thing as a perfect and stable control. So something we have to remind ourselves. Perhaps the solution is to use room temperature passivation, or use multiple control to really try to control the way we control our experiments. So to have multiple control seems to us the best way of doing things, and we've learned that the hard way in some ways. And with this, I'd like to acknowledge my co-authors and to thank you for your attention and any questions. Yes.
I've got two questions. First one is, what's the anneal conditions that you have? They just nitrogen?
Yes. You're talking about the float zone silicon?
Yeah, float zone will be...
Yeah, the float zone silicon, it's 1000 degree nitrogen, 1 hour.
And how about the CZ one, 3?
Yeah, the CZ was also nitrogen anneal, half an hour, above 360 degrees, yes.
And the second question is, have you looked at monocast material?
We haven't looked at monocast, but it's going to be obviously much more interesting because there's many more defects. Yeah.
Are there a lot of literature out there looking at monocast yet?
This literature is starting to build up, yes, on monocast. I guess the momentum is a bit lost on monocast recently because industry shift, I guess. But it's starting to build up, and it's obviously more interesting due to the dislocation and networks and the range of available material, the range of quality. But we haven't focused too much on monocast silicon. Yes?
So with your silicon nitride and aluminium oxide passivation with FZ wafers, were they as deposited lifetimes you showed, or were they annealed after deposition?
So for the silicon nitride, there was the as deposited passivation. For the aluminum oxide, we obviously had to do this 400 degree activation to activate the aluminum oxide, because it's plus minus atomic layer deposition. So it's after a 400 degree anneal.
So do you see the same improvements if you don't use nitrogen doping of the FZ?
No, we don't see, because it's already high lifetime. Yeah. So we don't see an improvement for the non-nitrogen doped float zone silicon wafers. But we see all other funny effects with the non-nitrogen doped float zone silicon wafers. Yes?
Yeah, two questions. Your defect, deactivation at 360 degrees, is of course something that is specific to that type of defect, that vacancy oxygen complex that you mentioned. Do you think that is sort of very representative for all CZ wafers? Of course, I would expect that if you have a different supplier growing at a different rate, or maybe even from the same supplier from a different part of the ingot, that a completely different type of defect would dominate, and then the deactivation temperature would also change. So do you have any comments on that? And is there any way to identify on the wafer what type of defect it is?
Yeah, that's a very valid point. What we've seen is that on this ingot, this defect was throughout the ingot, okay? But this was one particular ingot. So we are at this stage now where we're trying to investigate a range of CZ ingot to evaluate how widespread this can be. And potentially this is just for one type of ingot grower, and it's not relevant for other type of ingot grower. There's a lot of work to be done to really understand how widespread this is, and we're starting to do this.
Could ingot growers potentially decide to hold the ingot at 370, 380 for half an hour before they actually cool it down further to completely get rid of this defect?
That's a good point. That could be something that's done, and it could be a solution. I mean, you think that because the ingot is going through this very slow ramp down, this would be effectively the case, okay? But I mean, the experimental results are here. If we do this anneal, this is what happens. So maybe we need this. We'll need to reheat the ingot somehow. So because what we think could happen is that you have this ingot that's created at high temperature, then we cool it down, and when we reach this temperature of 360 and lower, we're pairing with all kind of vacancy pairs with all kind of defect. Like they pair with themselves, they pair with oxygen, they pair with potentially phosphorus, and then the only way to make sure that the vacancy oxygen is complex are deactivated is to reheat above that temperature, depair them, and then we're fine. But that's just one theory, and we're really at the early stages.
The other question I had was on your lifetime measurements. You said you're using bias light to activate the surface passivation. Is that right?
Yes.
And is that bias light on during the lifetime measurement?
No, it's not. No. So we shut it off just prior to measurements. Yes. So otherwise we'll have strange effects. And it's also interesting that the HF itself is conductive. So we have to do some corrections for the conductivity of the HF solution. We've done quite a lot of work, and Nick was working with me on this paper. We've done quite a lot of work on that. So we think that we're getting there.
So when you do the 360-degree anneal of the CZ material, can you regenerate that defect? If you reheat the wafers at high temperatures, do you regenerate that defect?
We attempted to do this, and unfortunately the furnace that we used was contaminated. So we ended up crashing the lifetime of all the wafers. So yeah, I'd love to know the answer, but we crashed the lifetime. So I think there was some kind of metallic contamination or other. So I can't answer you. But then again, we're doing more experiment on that right now. So maybe in a couple of months, I'll be able to.
The annealed lifetime is stable. So if you remeasure the sample and you just left it for
yes, the anneal lifetime is stable. The anneal lifetime is stable, and I do remember we trying to do some light-induced degradation, and we didn't see a change that I can remember. So the anneal lifetime is stable, but when we try to recreate the defect, we were unable to do so. So yes.
Well, in furnaces you use as a carrier gas nitrogen. So you say it's actually not good because nitrogen would then go and create defects, or like become recombination-active. Would it be better than to switch to helium or argon or something like that?
Potentially, yes. It would be. I mean, for low temperature, the diffusivity of nitrogen can be so low that effectively we're not going to incorporate nitrogen for like the 360 degrees or 500 degrees. For the high temperature, potentially we can incorporate more nitrogen, but yeah, it doesn't seem to be a problem. Yeah, I guess maybe nitrogen incorporation. I mean, they must go through the. Maybe if there was a film there, it will allow the incorporation of nitrogen more easily. But there's some kind of. It's probably hard for the nitrogen to get into the wafer in the first place, and again, 1,000 degrees, the diffusivity is not so high. It doesn't seem to be a problem for us. But that's a good suggestion. We could try this potentially because, as you've seen, the lifetime in the anneal state was lower than in the hydrogenated state. So potentially you're right. Potentially something there. Yeah.
Question? So let's thank Fiacre again.